Okay, welcome everybody. After a while, we continue our HEP-TN Seminar series. And today it's our great pleasure to welcome Erez Zohar from Hebrew University in Jerusalem. And he will tell us about gauge Gaussian fermionic PEPS, studying Hamiltonian lattice gauge theories in bigger than 1+1 dimensions using tensor networks and Monte Carlo. So yeah, please take it away, Erez.
Okay, great. So thank you very much, Johannes, for the invitation and for the introduction. Indeed, I'm going to tell you today about this class of tensor network states, which we call gauged Gaussian fermionic PEPS. And this is something which has been in the focus of very long ongoing work with several collaborators that I'm going to mention throughout the talk. I just want to mention that here we have Patrick Emmons from MPQ with us, and he has been working with me on that for the last few years on the numerical aspects, and he will also be here for some numerical questions if something very technical is required from the audience. So basically, these are states that we introduced several years ago, I think already 7 years ago or something like that, as an analytical construction, which something which could be seen almost as some sort of abstract class of states, which would be suitable for describing states in a lattice gauge theory in terms of tensor networks, in terms of PEPS. And over the years, what we learned is that besides some nice analytical features that these states have, they can actually be used as a tool as a numerical tool for actually optimizing, for example, and finding the ground states of some important Hamiltonians when combined with Monte Carlo techniques. So usually, as I will show you, one wants to use tensor networks in lattice gauge theories and in wider contexts to avoid some of the problems that are experienced by Monte Carlo methods, for example, the sign problem, especially when fermions are involved. But here, as we will see, the sign problem is not encountered because the Monte Carlo comes from another direction, which makes this method, when we consider it as a numerical method, it makes it look very beneficial. And I will conclude with some real benchmarking numerical examples in which we actually put it to use. So I will really tell it to you in a chronological way. We'll start with things that are very abstract and far from numerics, and narrow down to the actual use of the thing as a numerical tool, and see how it can be used. Okay, so why do we bother to look at gauge theories? Of course, these are very interesting models, and they appear in many contexts in physics. So in high energy and particle physics, of course, we all know that they are the description given to us by the standard model for the forces and interactions among matter particles. Also in condensed matter physics, they appear quite a lot. There are several models, for example, with finite groups, such as the toric code or quantum double models. Also, when the gauge groups are not finite, you can have some emergent or effective gauge theories. There are Chern-Simons theories, some candidates for ITC models. All these things and many others involve some gauge symmetries. So the mathematical framework is very, very similar. They're also challenging. Why? Because they involve some local symmetries, as I will describe, and having a local symmetry means that there are many constraints that must be taken into account. This can be very difficult sometimes. They also, in many interesting and physically relevant cases, include some non-perturbative physics. For example, if we look at particle physics, we have the well-known phenomenon of quark confinement, the mechanism which holds the quarks together and doesn't let them exist in the phase we see around us as free particles. This is definitely non-perturbative physics, and perturbation theory methods cannot be used for looking at it. And also in different phases of such models, for example, things that we call color superconductivity or quark-gluon plasma, there's quite a lot of non-perturbative physics that has to be handled somehow. So it's hard to treat this gauge theories experimentally in the non-perturbative case, at least, because there are strong forces which prevent us from doing some things we'd like to do. It's hard to treat them analytically. As we already said, these are non-perturbative models. And then people came up back in the 70s with the brilliant idea of putting everything on a lattice, and they introduced lattice gauge theory. And this was a gauge invariant way to regularize such models on a lattice. It was very useful for some analytics in the beginning, but eventually it was used, and it's still used today, as a very powerful numerical method that has given us a lot of what we know today about hadronic physics in QCD. So what are the conventional lattice gauge theory techniques, the numerics that people have been using all the time? First of all, you discretize both space and time as a part of the conventional attitude in particle physics to have things in an explicitly Lorentz invariant form. So you treat space and time on an equal footing. Then you would like to compute observables and correlation functions using path integrals. And in order to do that, you convert from the Minkowski spacetime to some Euclidean spacetime by going to imaginary time. In such a way, the integrals converge nicely most of the time. And then things can be given some statistical interpretation. There is some probability density given by this e to the minus SE, where the exponential of the Euclidean action. And when you have some statistical sampling, you can use Monte Carlo to solve the integrals. And so this has been very, very successful for many applications. For example, some static computations of the hadronic spectrum, the masses of the particles, the composite particles that we see in QCD. But it still faces some problems in spite of the absolutely great successes. First, it doesn't allow us to look directly at real-time evolution, since we work in a Euclidean space-time. So all the unitary time evolution operator becomes a decay factor. It's very useful for finding ground states and ground state energies, but it doesn't allow us to look directly at real-time evolution, at dynamics in Minkowski spacetime. Then there's also the very famous sign problem, a numerical problem that happens when you have fermions with a finite chemical potential quite often. In these cases, what we see is that what we would usually like to interpret as a probability density is no longer positive or sometimes not even real. And then we can't use Monte Carlo, and some other methods have to be used. On the other hand, it's very important to discuss such cases, such regimes, because, for example, finite density fermions is something that you have in many interesting phases that exist in the QCD phase diagram, such as color superconductivity. So it's important to find a way to deal with such physics. And new approaches focusing on these problems and trying to overcome them have emerged in the last few years from the, let's say, quantum community. One is the quantum simulation of lattice gauge theories, which is a very, very lively field at the moment, and we're not going to talk about it today. The other one is to use tensor network methods in order to address these problems. And this is what we're going to focus on. So when we study lattice gauge theories of tensor when we study lattice gauge theories with tensor networks, why don't we have a priori these problems? Real-time evolution is something that a priori is not prevented because we work in quantum Hilbert spaces. We use the Hilbert space picture. Time is a real coordinate. So even if some tensor network techniques are not well suited for describing time evolution, it doesn't mean that it's blocked in general. It's not like performing the weak rotation, which completely blocks the way and doesn't allow us to look directly at time evolution. The sign problem, very similarly, when you work in a quantum Hilbert space, fermions are fermions. You don't compute a path integral. You don't include some time direction. You don't have to represent your fermionic fields by Grassmann variables with integration. When you use the path integral picture, gives rise to the problem. Here you can use other techniques to deal with the fermions without going through path integrals and Grassmann variables, which a priori don't necessarily have to see the sign problem. So these are some nice potentials that we have when we want to use tensor networks. So of course, if we want to look at it at some chronological perspective and see what has been done in the past in this field. So first of all, people looked at MPS, matrix product states, and tried to see how it can be used for lattice gauge theories. So matrix product states, when you combine them with DMRG, density matrix renormalization group, have been really successfully and widely applied in many body models, in particular in condensed matter. This is a very powerful numerical technique, which works well in one space dimension. And this was also applied quite successfully to lattice gauge theories in one space dimension by several groups and collaborations. First of all, in the first works that these people did, they used tensor networks to compute things that were computed previously in the conventional methods, to benchmark the methods. And after this worked very nicely, for example, for models like the Schwinger model, they managed to move on quite impressively and also look at problems that couldn't be solved in different methods. So this worked quite nicely, even when you have finite chemical potential for the fermions, and even to demonstrate some real-time evolution effects, such as string breaking, for example. But then the question is, what can one do in higher dimensions? Because DMRG in general scales badly when you go to further dimensions. And the question is how we can overcome that and still use tensor networks in higher dimensions to study gauge theories. So I want to give you a very brief overview of what has been done in the field of Hamiltonian lattice gauge theory tensor networks in more than one space dimension. And look at this little footnote. There has been a parallel approach called TRG, Tensor Renormalization Group, or tensor field theory, in which tensor networks have been constructed to look at path integrals. And this has also been very successful for many things. But here I'm talking about Hamiltonian lattice gauge theory states in Hilbert space. So I'm not going to talk about this directly. So 10 years ago already, Tagliacozzo and Vidal considered some tensor network construction of a Z2 pure gauge lattice gauge theory. And a few years later, also something more general, some general construction for tensor networks and for lattice gauge theories with arbitrary continuous groups was introduced by Tagliacozzo, Selye, and Levenstein. Now, at this point, people started talking about gauging. What do we mean by gauging? As we will see, a particular type of tensor network that I will briefly introduce today, PEPS, allows one to deal with global symmetries in a very easy and natural way. And then at this point, around 2014, the idea of gauging PEPS has emerged, and what people are doing here is to take PEPS with a global symmetry and perform some sort of minimal coupling on the state level, lift the global symmetry to be local in a way that allows to introduce gauge field and lattice gauge theory states. So it was first introduced by this collaboration in 2015, in which they suggested how to gauge theories with Higgs-like matter. And shortly afterwards, we introduced a way to do it with other types of matter fields, including fermions, which is the basis of what I'm going to talk about today. Out of this work, we started producing some toy models with fermionic PEPS coupled to gauge fields that I'm going to talk about today. And there we saw some nice qualitative physical behavior expected by such models. And later on, what we managed to show is that this could be used for numerics. So these works, which are framed here, are the things that I'm going to talk about today. But of course, this discussion is incomplete without mentioning the parallel path that have been carried out in the last few years for Hamiltonian lattice gauge theories. So of course, some works on IPEPS were done. And also recently, we've seen these nice works with 3 tensor networks, which have also been applied to 3 space dimensions. But I'm going to focus on PEPS, the things that I briefly mentioned in the previous slide. Okay, now let's get, after this introduction, let's get into the physics and some more particular and technical details. So what's the Hilbert space that we are dealing with when we have a lattice gauge theory? First of all, unlike in the conventional approach to lattice gauge theory carried out by most people up to now, we discretize only space. So time is a continuous and the real coordinate. But, sorry. Very, very similarly to what you see also in the Euclidean approaches, we have 2 types of degrees of freedom. Matter particles, which are usually fermions, reside on the vertices or the sides of the lattice, and the gauge fields reside on the links of the lattice. We work in the Hamiltonian picture, so everything resides in some Hilbert space. And this is a very natural way to describe constraints which appear here quite naturally, as we will see. Now, in the core of gauge theories, we have the gauge symmetry. And we define gauge transformations as follows. These are some operations, some unitary operations, which act on both kinds of degrees of freedom that we have on such models, on the matter degrees of freedom, which are red in this diagram, and the gauge field ones, which are blue. By local, we mean that on each point of space, on each side of the lattice, we can act separately and independently with a different transformation, a transformation which will affect only the matter degree of freedom on the site and the gauge field degree of freedom on the links around it. And on each such site, we can pick, what do I mean by using a different transformation? As usual in physics, the symmetry is described in terms of group theory. So we have some symmetry group, which we call the gauge group. And the locality means that on each point, on each side, we can act with a transformation parameterized by a different element of the gauge group. And gauge invariant states are states that will be invariant under each such local transformation separately for each group element that I choose independently on each lattice site. So when I have a symmetry, something is conserved. So we can express everything in a very complicated way using this gauge, some basis we define on the links in terms of the group elements. But eventually what this symmetry means is that our physical state psi is invariant under some gauge transformation, this theta g of x, for every choice of x and for every group element g. So we can really act with a different transformations on different lattice sites, and we expect the states to be invariant. If the symmetry is continuous, we can express this transformation in terms of its generators, and then we get something which we can call a Gauss law. The invariant states are annihilated by the generators of this transformation. They all commute with the Hamiltonian, and this gives us something which looks like the Gauss law. You see we have here some divergence of L and R. These are some electric fields that I can define on the links around the site, minus the charge of the matter at the center. So having the symmetry means that the state is annihilated by all these local generators, and that means that all our physical states are eigenstates of that, which means they satisfy the Gauss law. Now, how can we obtain on the lattice? What's perhaps the simplest way we can obtain a lattice gauge theory? Imagine that we have a lattice model of fermions. So on each lattice site, we can either have a fermion or not. And the fermion on each site, X, is created by the operator psi dagger and annihilated by psi. And we consider this very simple Hamiltonian with this local term, which can be associated with mass, for example, and some hopping of fermions between nearest neighboring sites. A very simple Hamiltonian, it's not even interactive. And such a Hamiltonian is the following global symmetry. If I take all my annihilation operators psi and shift them with respect to the same phase, the same parameter alpha everywhere, the Hamiltonian will not be changed. It's a global symmetry. What if I want to make this symmetry local? That means that I want this parameter to depend explicitly on the site. So I put a different phase on each lattice site. Okay, I act only locally, different transformations on different sites. Then, of course, the mass term, which is local, will be invariant, but in this hopping term, can you see my cursor, Johannes? Okay.
Yes.
So thank you. So in this hopping term, we will get two different phases, which in general will not cancel each other, and so it's not locally invariant. To fix this, we introduce another degree of freedom, which we call a connection, this U operator, which resides on the links. So on each link, we introduce an extra Hilbert space on which these U operators act. And when we put it in the Hamiltonian like this, and then we add to the transformation, we have this transformation rule for the fermions, and we add the following transformation rule for the connection operators, for the U operators on the links. They are shifted by the phases associated by both sides of the link. When we put it into the Hamiltonian and we consider this transformation, the Hamiltonian will be invariant. So this is what we call minimal coupling or gauging of the Hamiltonian, and I'm sure that many of you are familiar with that, at least in the continuum. And this gives rise to a local symmetry, to a gauge symmetry. And so this is the picture that we saw before. We have the fermions, the matter particles, which reside on the sides, and we introduce the connectors, which are nothing but operators representing the gauge fields, which reside on the links. And in this case that I showed you is the U1 gauge theory, because the U is simply the exponential of some phase. This is something which behaves like a U1 group element. And this phase plays the role of a compact vector potential. If we write everything properly in the continuum limit, we will get QED. And since it's a phase operator, the conjugate operator will be something with an integer spectrum, like some angular momentum operator. On the other hand, with the gauge theory interpretation, the conjugate quantity to a vector potential would be an electric field. So phi plays the role of the vector potential, and L is the electric field. And with this compact way of formulating that, we will see that L, the electric field or flux, takes only integer as an integer spectrum. So we can denote its eigenstates by integers. And the U operator, this can be shown from this canonical relation between L and phi. The U operator simply raises the electric field on a link by 1. That's it. So if we want to have, what's the dynamics that we have here? We saw that we had this psi dagger U psi term. And what that means is like that, given what I showed you in the previous slide. We have a particle which hops, a fermion, which hops from this side to that side. And we have the U operator in the middle. And what it means is that it raises the electric field on this link. When the fermion hops, it raises the electric field by 1. So when the fermion moves, something happens to the electric field in the middle. And this, as we will see, accounts for the gauge symmetry or the Gauss Law. One can also add to the Hamiltonian some terms that will give rise to dynamics of the gauge field. So we have the electric energy term, and one can add some magnetic energy term. But these are things that I'm not going to focus on this talk. So let's skip that. The important thing is that indeed, when we have a symmetry, we have a conserved charge. So in this U1 case, what it means in the continuum, it means that we have this Gauss law operators, which generate the symmetry, the divergence of the electric field on each side, minus the charge having to do with the fermions on site is some conserved quantity. And in this lattice case, what we have is that the lattice divergence of the electric field, which are the L operators around each side. So I take the ones in the positive directions with the outgoing directions with a plus sign, and the ones on the ingoing directions with a minus sign, and I subtract the charge. This generates the gauge symmetry. This commutes with the Hamiltonian, and hence it gives me a set of local constants of motion. With this very brief description of the Hilbert space, we can start talking about the tensor network construction. What I'm going to consider here is PEPS, projected entangled pair states, and I will remind you that by that we mean that it's a particular tensor network construction that, first of all, for our purposes, it's nice to use it because it allows to encode and treat symmetries in a very natural way. We will see it. It also has, as other tensor networks construction, a bipartite entanglement area law by construction. And hence it means that it's suitable for describing physically relevant states like ground states of local Hamiltonians, etc. And it also offers some approaches. It comes with a nice toolbox that makes it easier sometimes to study phase diagrams and other properties of many body systems. And we might look at that too if we have time. So in one space dimension, this goes down to matrix product states, which, as I already mentioned, have been used quite successfully for lattice gauge theories. In further dimensions, sorry, we call it PEPS, but the idea is very similar. How do we, sorry. How do we construct these states? We build this PEPS, this particular kind of tensor networks, by contracting some local objects with one another. So first, let's look on a single lattice site. On a single lattice site X, we include the physical, we look at some object which includes the physical degree of freedom that we have on this site, maybe the matter particles which reside there or something like that. And we also introduce auxiliary Hilbert space, some extra degrees of freedom which will be used for the contraction, for connecting this site with the other sites. So in this case, I'm going to demonstrate with a square lattice in 2 space dimension. I'm going to connect this site to 4 neighbors. So on each of them, in order to do it, on each of them, I draw such a blue leg, and on each such leg, I introduce one such auxiliary Hilbert space. And for now, this auxiliary space can be arbitrary. Eventually, when I want to construct a meaningful state, I will have to specify what it is. But before trying to do anything, the physical Hilbert space is given to us by the theory we want to study. And the auxiliary degrees of freedom, they can be arbitrary before we actually want to do something. So on each side, we have this object with the physical and virtual degrees of freedom. And I write it down in the following way, which will be useful yet later for discussing fermions. I start with some initial or vacuum state, if you want, of the site, and I act on it with some operator A involving some operators which generate some state on this particular site. So, for example, if I work in second quantization, this A can be some function of raising operators of all the modes that I have here, physical modes in the center and auxiliary modes on the legs, and omega will be the Fock vacuum, bosonic, fermionic, both. Then what I do is that I put such an object on each lattice site. So I have here a general vacuum state of my lattice, and I act on it with a product state of A operators, creating some local states on each site. At this point, the sites are disconnected. I just have some product state. I have no correlations between the sites, no entanglement, nothing. But of course, that's not what I want to study. And I also have too many extra degrees of freedom, all the auxiliary ones, which are non-physical. So what I'm going to do is that I'm going to project the auxiliary degrees of freedom on the 2 sides of each bond of my lattice onto some maximally entangled state, which is symbolized here by this green ellipse. As a result, and this is something which is represented here in terms of this project of omega L, which are some projectors on the links, and I project back to get rid of these spaces onto the vacuum state of the auxiliary of virtual degrees of freedom. As a result of that, I create correlations, and not just correlations, I create some entanglement between the different sites, and I also get rid of all the auxiliary degrees of freedom. So I'm left with this state psi 0, which includes only physical degrees of freedom. They are the only ones which are not contracted. And I have some physically relevant, let's say, correlations between the sites. What are these physically relevant correlations? It's basically entanglement area law. This is satisfied by contraction, because if I make some bipartition of this lattice, I can see, thanks to the special way I connect the sites with the projection onto maximally entangled states on the links, that the contribution to the entanglement between the inside and the outside will come only from the links who cross. They all give rise to the same amount of entanglement, and we get the area law. This is not new. I just wanted to remind you that. Another thing which is not new is that PEPS are very useful for parameterizing states with a global symmetry. Why? I can demand my the ingredients of the PEPS to satisfy these following 2 properties. I can say that if I act, I choose some group, and I want it to be the symmetry group of my state. I want the state to be invariant under global transformations parameterized by this group. And I can parameterize the state by solving this equation. I say that acting with a group transformation on the physical degree of freedom equals acting with group transformations parameterized by the same group element on all the auxiliary legs. There are some more technical details. You have to put daggers and things like that sometimes, but that's the general idea. that acting on the physical degree of freedom can be traded by acting on the virtual degree of freedom. If I demand this, and I also demand that the projectors are invariant under these group actions from both sides, I will get a state with a global symmetry. And let's see why. Here I have my PEPS psi 0, which I constructed as in the previous in one of the previous slides, and I want to act on it with some global transformation parameterized by this group. That means that I act on all the physical sites with some unitary parameterized by the same group element. That's the meaning of a global transformation. However, since I have this symmetry property with which I parameterized my PEPS, I can trade the physical action by these auxiliary actions. Then, since I have the other symmetry property, which means that the projectors are invariant under these actions, I can completely remove these objects, and I get that my state is invariant. So that's a way to parameterize the PEPS such that it will be invariant under a global symmetry. Now, if we take a look at it carefully, we can see that it's very similar to the gauge the concept of gauge invariance in lattice theories. What do I mean by that? In the PEPS, we got the symmetry, the global symmetry, by demanding that acting on the physical degree of freedom on site will be equivalent to acting on the legs, the auxiliary degrees of freedom. And when we consider a gauge theory, we have the following relation between the matter degrees of freedom on the sides and the link and the gauge field degree of freedom on the links. We say that the state is invariant under acting on the matter and the link and the gauge fields on the links around it. So it's a very, very similar situation mathematically. The difference here is that on the right, in the lattice gauge theory case, what we have on the legs or on the links are also physical degrees of freedom. And in this PEPS case, what we have on the legs or on the links, these are just auxiliary objects. And this property is used before we contract. And after we contract the sites with one another, we lose this local property, but we get a global property. Yet it's very, very similar. So can we use this in order to lift the global symmetry to be local? And the answer is yes, we can. I'm sorry for stopping all the time. I got a little cold. So how do we do that? How do we do that thing which can be thought of as performing the procedure of minimal coupling that we saw for Hamiltonians before on the level of a state? We can't do it in general for arbitrary states, but with PEPS we can. And let's see how. We start with the following PEPS construction with the following local ingredient, as I showed you before. And we want to lift the virtual symmetry to be physical or the global symmetry to be local. So first of all, in the first step, we introduced Hilbert spaces for the gauge fields on the links. We introduced more physical degrees of freedom, and we just prepare them in some idle initial states, for example, electric field 0, and put them in a product state with our PEPS. Okay, we have extra Hilbert spaces, but they are not coupled with our state yet. It's just some product. In the next step, we wish to entangle the auxiliary degrees of freedom on the outgoing links with the newly introduced physical Hilbert spaces representing the gauge fields on the same links. By that, so it means that I act with the following transformations that I call gauging transformations. And by that, I sort of, I have some Gauss law satisfied by the auxiliary degrees of freedom with some virtual electric fields if you want. And I want to convert it to a Gauss law of the physical electric fields. So I can write down some unitaries that will map the information of the auxiliary electric fields to the physical ones that I introduced. And then I convert the virtual Gauss law that I add into a physical one. So for example, this can be done in the U1 case. I can also do it with other theories. Let's not get into these details because we don't have a lot of time. But what it means in general is that we perform the following. I start with a PEPS, which was parameterized to be globally invariant under some group. So it satisfies this property from the left, acting with the physical transformation on the center equals acting with virtual transformations on the legs around it. By performing the gauging procedure that I showed you, we get, instead of that, the following three properties automatically, which means that if I act on the matter side and the two electric fields in the outgoing links in a particular way, it's equal to acting on the auxiliary legs, and also with other actions on the electric fields alone, it will be equal to acting on the auxiliary electric fields on these directions. So now let's see why it gives us some local symmetry. Now I have this PEPS this new PEPS, this gauged PEPS that I constructed, and I want to act with a local transformation. That means that I don't have these yellow circles everywhere. I only have them around one particular link. I act one particular site. I act on the matter degree of freedom and the four links around it. Why is this going to be invariant? So first of all, I have this symmetry property thanks to the gauging. This allows me to trade 3 of the 5 physical operations by these 2 virtual ones. Then I also use the other kinds of symmetry properties that I got out of this gauging. And this allows me to trade the remaining physical operations by these 2 auxiliary ones. The projectors are invariant as before. We didn't change them. We didn't replace them by anything else. So I can just drop these virtual transformations, and I get that my state is completely invariant. So by performing this gauging procedure, introducing the extra physical Hilbert spaces on the links and properly entangling them with the auxiliary degrees of freedom on that links, we get a locally invariant state. We inherit a state including matter and gauge fields, a state of a lattice gauge theory that will in general be an interacting state out of some globally invariant state of the matter alone. Now, this we want to apply for studying a particular class of models. We want to build, first of all, PEPS, including fermionic matter and dynamical gauge fields, because this is pretty much the situation that we have if you look at the standard model, for example. The matter fields are usually fermionic. So the starting point for us would be Gaussian fermionic PEPS with a global symmetry. Why? First of all, what are Gaussian states? Gaussian states are ground states of quadratic Hamiltonians. They are free states. They can be completely described in the fermionic case in terms of their covariance matrix, and they are very, very easy to handle analytically if you use the so-called Gaussian formalism. And actually, very recently, there appeared a great paper by Luca Tagliacozzo and his student, I think, on fermionic Gaussian states, and you can see everything there. Fermionic PEPS are PEPS, which are defined with fermionic creation and annihilation operators. Basically, the construction that I just showed you with fermionic degrees of freedom. And these are very easy to parameterize if you also make them Gaussian. And this was something that was introduced 10 years ago in this PRA by Christina Krauss and collaborators. So we want to build in the starting points fermionic PEPS that are Gaussian, very simple states that are not even interacting. And we want to make them invariant globally under some symmetry group. Then we carry out the gauging procedure that I showed you and add some gauge field. Why is this interesting? It's similar to minimal coupling that one does to a Hamiltonian or a Lagrangian. in general quantum field theory cases. You start with a free theory, with a free state of the matter, in this case, the Gaussian fermionic state. And then you perform the gauging procedure, and you perform a state, an interacting state, including both the matter and the gauge field. So first of all, before we say anything else about these states, from a pure intuitive point of view, these states seem useful for studying lattice gauge theories because we do something similar to what's done in other approaches. You start with a state, you start with a free state with a global symmetry, you leave the symmetry to be local, and then you have the gauge field in the picture. Let's try to use this as an ansatz. First of all, we have to check if it's indeed a valid thing to do. So at first, we just constructed some toy states for some toy models and examined the physics that they manifested to see if there's something which looks similar to what you have in conventional gauge theories. So we considered U1 and SU2 fermionic PEPS, one abelian example, one non-abelian example. We constructed some minimal instances states with the smallest possible auxiliary Hilbert spaces, parameterized them to have the right symmetry, U1 or SU2 symmetry in these two cases, a global symmetry. I'll skip this technical details of constructing the PEPS. Basically, we demanded this property which relates the physical transformation with the virtual ones. And at the end, we arrived at very simple states which depend on very small sets of parameters. Okay, these are Gaussian fermionic PEPS with either a global U1 or a global SU2 symmetry. Okay, we don't expect them to contain all the possible states relevant for studying real lattice gauge theories. For such states, you'll have to increase the virtual degrees of the Hilbert space and so on. This is just for was done merely for the purpose of constructing something with the symmetry and this method and see if it manifests some interesting physics. So we gauged these states. We started with something with translation invariance. When you properly gauge it, it becomes charge conjugation. Rotation invariance remains. And as I already explained to you, the global symmetry now becomes local gauge invariance. The auxiliary Gauss laws become physical Gauss laws. Okay. Now, how do you study such states? What we did was to use a cylindrical geometry. And when you have a cylindrical geometry, you can easily convert it effectively to a one-dimensional system by contracting the rows. Then you can construct some transfer matrix containing the row contribution for the cat and the bra, just like you do normally with the matrix product state, for example. And any correlation function can be obtained as some product of this correlation of these transfer operators. And then, roughly speaking, a gap between the two highest eigenvalues of the transfer operator corresponds to some exponentially decaying correlations in real space. So such a transfer operator can be used as some probe for phase transitions. When you also have some local symmetry in your theory, you will need to consider another type of a transfer operator, because you can't compute two-point functions or correlation functions in a gauge theory unless the two separate operators are gauge invariant independently of one another. Otherwise, you need to connect them by some flux operators, some strings of the gauge field, and this means that you have to define another kind of a transfer operator and also check its properties. But making a long story short, at the end, we were able to draw some phase diagrams, which means here diagrams of the gap of the transfer matrix for different choices of the parameters on which the state depends. and the lines where the gap closes are the ones that are suspected as phase transitions. In order to understand the different physics that you have in each gapped region of this diagram in parameter space, you need to compute some order parameter and consider its behavior. So for example, in the case of pure gauge theories, the relevant order parameter is the Wilson loop, some oriented product of gauge field or operators along closed loops. And in the thermodynamic limit, when you consider this rectangular loops, for example, if it decays in a way that's proportional to the area, it means that static charges are confined. It's a confining phase. And if it's a perimeter decay law, it corresponds to the confinement. This was pointed by Wilson in the 70s in the first paper that introduced lattice gauge theories. So this is one operator that is one observable, which is meaningful to compute when you want to understand what's within each phase. And actually recently, in jumping to the future, to the last year, I also studied in a newer work how one can relate the Wilson loops to properties of the local tensors using these transfer matrices, and what the local symmetries impose. They impose very strong conditions on the structure of the transfer operator, and this can simplify the computation, the tensor network contraction, and also tell us, just by looking at the single site, whether we would have an area law or a perimeter law of the Wilson loop. There are some rules for that. Sorry. But the bottom line is that if we take it back to the old toy model states and we compute the Wilson loop in any of these gapped regions of the parameter space, which we obtained using the spectrum of the transfer matrix, we see that in some of them, the Wilson loop decays in a way that is proportional to the perimeter, and in others to the area. So we do see in such a, already in these toy model states, we see some interesting physics. We see confinement and we see deconfinement. And this is a first good sign that these states can describe interesting physics. Then we also used some other techniques of the PEPS to draw these phase diagrams analytically, and also considered some other observables in the U1 and SU2 theories. But what we discovered later on is that these states are also useful when you actually want to do numerics. And how do we do that? So naively speaking, when we consider a gauge theory, we might want to say that the Hilbert space would be a product of the Hilbert space of the gauge fields on the links and the Hilbert space of the matter fields on the sides. However, this is not true. The Hilbert space is just a subspace of this product space. And this is because we have the local symmetries, we have the Gauss laws, we have local constraints satisfied by the gauge fields and the matter fields, which tell us that only very particular configurations are physically relevant. So only some subspace of this big product space is relevant for us. And this we can actually exploit in a way that will help us now to contract these PEPS. So I want to define the following states, which I call gauge field configuration states, as follows. Consider a state, so on each link of my lattice, I have the Hilbert space of the gauge field, and I can span it in terms of states labeled by elements of the gauge group G. So this capital G, the gauge field configuration state, is some product states of different group elements on different sites. Okay, for each choice of different group elements on all the sites, I can define a different gauge field configuration state. And then I can find define some integration over it as the product of group integrations of integrating over the group element on each particular site, which is labeled by the starting point X and the direction K. So a general state in this product space, before demanding the gauge invariance, I can always express as follows. I integrate over the different configurations of the gauge fields, and then I have, for each configuration, I have such a product state, the gauge field configuration state, and some matter state, psi of G, where G is a parameter, just labeled by it. And this actually looks like some Schmidt decomposition, where the Schmidt index is the group configuration. Of course, if I have the gauge invariant and it's not just some arbitrary state in this matter field, there will be some relation between the gauge field state and the matter state for each configuration. And this is another thing that we're going to use. So when we express the states in the magnetic basis, we can actually perform some efficient Monte Carlo configuration. Why? We defined the gauge field configuration state like this. These G states are normalized. So there is some orthogonality relation satisfied by this group configuration states. The overlap of two configurations is 0. The overlap of the same configuration is some delta function. It can be Kronecker delta if the group is finite, or some distribution if the group is continuous. And psi G will be some matter site depending on that, depending on the configuration G. But obviously, if we can express any gauge invariant state in this form, we can also do it for gauged Gaussian fermionic PEPS. And when we do it for these states, then the state psi G will be some Gaussian, some fermionic Gaussian state, which describes fermions coupled to some static field, to some background gauge field G. So I expand my state in terms of products of the gauge field configuration states, which are very simple states, easy to handle, and fermionic Gaussian states. They are not translationally invariant in general because they see some arbitrarily complicated gauge field configurations, but they are Gaussian. So each psi alone is non-interacting and easy to handle. And we consider this complicated combination of these states, which is not a free state in general and something which can describe some interesting physics. Why is this good for numerics? For example, consider the Wilson loop, an observable that we want to compute. It's the product of some gauge field operators along the links of some closed path. This group configuration states are eigenstates of these Wilson loop operators. So when I want to compute for example, I have an operator like this. The Wilson loop can be a very complicated operator made up of gauge field operators all around the lattice. And I want to compute the expectation value with respect to this state expanded in this way. Since the gauge field configuration states are eigenstates of the Wilson loop operators, when I act with this on such a state, which I need to do when I want to compute the expectation value, I can convert each of these operators to some numerical function depending on the particular gauge field configuration. And then the expectation value of the Wilson loop can look like this. I integrate over the gauge field configuration. I have here some function which might be complicated by some classical function of the gauge field configuration representing the observable I want to compute. And then I have the norm of this field, and I divide by this normalization factor. But note that this thing in yellow here always defines some probability distribution. It's normalized, and it comes from the norm of a state, the norm of a quantum state. So it will always be real and it will always be positive. It can't give rise to any sign problem. It's a probability density. Furthermore, if the psi-g states are Gaussian, as in our case of gauged Gaussian fermionic PEPS, it means that computing the norm is very easy and very efficient. You can use the Gaussian formalism for that. So that means that you can compute this expectation value of the Wilson loop, this is the observable I'm now demonstrating with, quite efficiently and easily using Monte Carlo integration without seeing the sign problem. What about other observables? Obviously, the Wilson loop is not the only interesting observable that we have in such theory. The nice thing is that any observable we'd like to compute, we can express in a similar form using classical functions of the gauge field and either the norm of the fermionic Gaussian states or elements of its covariance matrix, which is also something with computation comes quite easily and efficiently for us when the psi of G is Gaussian. So eventually, what we see here is that we can actually compute expectation values of physically relevant observables of gauged Gaussian fermionic PEPS. Even in more than one space dimension, the dimension doesn't, things don't depend directly on the dimension, or the scaling doesn't depend terribly on the dimension as other methods using this trick. So first of all, again, we want to consider some toy models and see if things make sense. So the first check we did already some years ago was to revisit these toy model states and try to compute observables using this technique. And we saw that physical observables add some jumps, some non-analyticity, exactly on the same lines that were suspected as phase boundaries when we use the transfer matrix gap trick. So that's a good sign that things are going well. Eventually, what we wanted to do is to use it as a benchmark, is to use this method for studying some real physical model. What do we mean by that? We wanted to take some real Hamiltonian, which is interesting in the context of lattice gauge theory, and find its ground state using this technique, using this state. So what we did was to look at a pure Z3 gauge theory. It's a theory without matter, it's pure gauge. And the Hilbert spaces on the links are three-dimensional. And one can define these Z3 operators. I won't get into these details, but it's one particular example of a lattice gauge theory. The Hamiltonian depends on a single parameter, this G, this coupling constant, which sets the ratio between this local part in terms of the links, which has to do with the electric energy and the four-body plaquette interactions of the magnetic energy. And what we did was to vary this G, and for each choice of G, we performed some variational computation, or some variational Monte Carlo, to find the ground state where the ansatz states were these states that I just introduced, the gauged Gaussian fermionic PEPS. So here are some results. First of all, before the Monte Carlo, some exact contraction, which shows that these states are actually meaningful. So we are looking here at some very small system, 2 by 2 plaquettes, and this blue curve shows the exact diagonalization of this Hamiltonian for different values of the coupling constant done by Patrick. And in this orange dots here show Patrick's computation with such states. Basically, what he did was to take the simplest construction of a gauged Gaussian fermionic PEPS with this Z3 symmetry with the smallest possible virtual Hilbert space. That's what's referred to here by one layer. And for each G to look for the parameters of the PEPS giving rise to the ground state. Simply minimizing the energy as a function of the parameters on which the PEPS depends for different values of the coupling constant. So with this minimalistic choice, what we can see is that, so this is without Monte Carlo even, okay? It's a simple, small system in which you can just exactly perform all these integrations, which in this case become simply sums because it's a finite group. So first of all, with the most minimalistic PEPS, we see that it works very well for large values of the coupling constants. But once we meet this point of that takes us between strong coupling and weak coupling, the PEPS description breaks down. But no problem. We can just increase the dimension of the auxiliary spaces, which I told you we can control them and increase them as we wish. And if we enlarge them, we just gain more variational parameters, which can help us probe more physics. So you see, if we double the auxiliary space, what we could see is that we could actually probe into the weak regime. And with more and more layers, which means increasing more and more the dimension of the auxiliary spaces, we could actually go deeper and deeper into the weak limit physics. So that's for exact contraction. What about Monte Carlo? So this is already a Monte Carlo plot, considering computations. So here what we have on the vertical axis is the expectation value of the Hamiltonian for the points found as ground states, for the points which minimize the energy, normalized by the size of the system, which was 2 by 2, 4 by 4, 6 by 6, 8 by 8, compared with the exact diagonalization plot for the small system that we have here above. And what we could see is that actually it works. Basically, we can see that at points that are far from this phase transition, and this is expected when you study PEPS, which are in general not suitable for critical physics, we see that we managed to find the right ground state, to compute the right ground state energy. So there are states within the class of gauged fermionic Gaussian PEPS we constructed this way, which are either the real ground state or close enough to the real ground state of this Hamiltonian. And of course, we see that as we go deeper and deeper into the weak regime and enlarge the system, things work a bit worse, but this can be compensated by enlarging the virtual spaces, and it really allows us to probe into the weak coupling regime. And this for us is really a benchmarking conclusion, something that shows us that these states are very useful for studying lattice gauge theories with real Hamiltonians. And now we are working on improving the numerical methods and taking it to more physical cases, to other gauge theories, other physical scenarios with fermions too, etc. So in conclusion, what I wanted to show you today is that PEPS, which are very useful for describing globally invariant states, can be generalized to lattice gauge theory states, to states with a local gauge symmetry. And then that using the PEPS construction, we can actually gauge states or minimally coupled states, something which doesn't exist for arbitrary states, but we can do with PEPS thanks to their special construction. So if we parameterize a PEPS to be invariant only with the meter degrees of freedom, to be invariant under some global symmetry group, we can apply a well-defined procedure and inherit from this parameterization non-trivial states of a lattice gauge theory, including both matter and gauge fields with the local symmetry. And eventually what we saw is that when the states we gauge are Gaussian fermionic PEPS, then we get this gauged Gaussian fermionic PEPS, which can be useful for studying numerically using variational Monte Carlo lattice gauge theories in more than one space dimension without encountering the sign problem. And if you're interested in more details about it, you can have a look at these lecture notes that we wrote a few years ago. And I think that's all I had to say. So thank you very much, and sorry for my little breaks in the middle.
Thank you very much for this very nice talk. It's no problem for us with breaks. Yeah, I guess there are questions, so please, if anyone has questions, then just speak up. Maybe I actually can start. The first thing, maybe a bit notation. When you talk about compact QED in the beginning, what is the term compact actually referring to?
So it refers to the fact that the vector potential is a compact variable. So instead of having some A, which in general is a real field, which can take every real value, you have an angle, which is bounded and periodic between 0 and 2 pi.
I see. Okay. And yeah, another thing that I would be interested in is when you saw a confinement or deconfined phases in your toy model for different parameter regimes indicated by the Wilson loop or the either area law or perimeter law, then if I catched it correctly, this was an abelian gauge theory, which
I showed you some demonstration for the abelian one, but we also looked at we also constructed some SU2 example, which you can see here.
Yeah.
And in this particular one, we always had perimeter law, and one phase was gapped and one was gapless. But I believe that the reason we didn't see an area law here is just because it was a very small set of parameters. The state depended on a very small set of parameters.
Well, right, but there was also a confined phase in the abelian theory, right?
Yes.
So
here you can clearly see some area law.
Right. So I'm surprised because I thought, like in the QCD context, for example, confinement is only in the non-abelian theory.
So this connects very well to your previous question about what's compact, because when you take this to the lattice with the compact formulation, okay, what you get, this is something that I skipped, but we can talk about it now. What you get is that the magnetic term, okay, which is quadratic in the continuous case, becomes in the compact case, in this particular discretization of the theory, a very non-trivial four-body interaction. You see, I have here an interaction of this phi, the compact vector potential, on all the four links around the plaquette. Okay, so this is something which actually can generate. So this is already one very big difference between the lattice model and the continuum model. Okay, because if you think about pure U1 theory, okay, in the continuum it's solvable. You can just solve it in terms of photons. But on the lattice, it's a very non-trivial model with this nonlinear four-body interaction. So this gives rise to a very different kind of physics. And what you can see in such models is that they actually have confinement under some conditions. So in the strong coupling regime where this is switched off, you can even use perturbation theory and show that for any gauge group and any dimension, you get confinement. And in other cases, you will also have confinement even when the magnetic term dominates. For example, it was shown in different ways back in the 70s that due to some topological effects, you'll have confinement in compact QED for all the values of the coupling constant. And indeed, this is something that you don't see in the continuum. But on the lattice, it exists. And one of the great things that you get out of it is that when you actually want to study these quantum techniques, either tensor network states or quantum simulators for lattice gate theories, and you want to study something non-perturbative such as confinement, it's enough to begin with an abelian model, which is usually much simpler to construct. It will already show you, at least qualitatively, this non-perturbative physics that you want to study. And it's very, very useful when you want to start applying a new set of tools to address such things. You don't have to run to the non-abelian cases in order to understand how to probe confinement and other non-perturbative things for lattice gate theories using these techniques.
But I'm a bit skeptical because the confinement is here a lattice effect. And at the end of the day, we want to study the continuum. So if you see confinement here, I would call it unphysical because it doesn't exist in the continuum. So
you can call it, yes, that's true. But I'm talking here as using the abelian cases, okay, as some test bench for the methods you want to use for finding whether you have confinement or not. For example, take a pure gauge theory. You want to see if it confines static charges or not. You will use the Wilson loop in the abelian case or in the non-abelian case, doesn't matter. And measuring it in a quantum simulator or computing it using tensor networks will be using, at least qualitatively, the same methods whether it's abelian or non-abelian. So when you want to develop a method that will be used eventually for, let's say, QCD or some simpler non-abelian theory, SU2 or something like that, having the possibility to see how you handle and measure such effects with simpler abelian models is very useful. Okay, you don't have to do it on the first step with the full complicated model. You can start with something simple. So yes, I agree with you. Studying confinement using these tools for QED is not interesting for studying continuum QED, which is what we'd call physical. But it would be highly relevant for understanding how to do it in the non-abelian case, which we can then use for deducing something on the continuous case.
Let's see. Okay, yeah, please. Are there other questions in the audience?
You're muted.
Sorry, one of your pictures was about t equal to 0 and t equal to 1. As the picture is different, so how it's possible?
So I didn't.
In two cases, t1 and t0.
I guess you're talking about. Let me go there about this.
Yes. Yes.
So I didn't get to explain the roles of these states here dependent on 3 parameters, t, y, and z. And I didn't get to explain what they were. So basically this little t, which is 0 and here 1 as an example of non-zero, this is something which has to do with coupling the physical degrees of the physical fermions and the auxiliary fermions. So when I set T to 0, it means that I have no physical fermions, and that means that I'm in a pure gauge theory. When I set it to 1, I have both gauge fields and physical matter in my state. So these are basically different models with different physical contexts. Then you get different plots.
Question, if I may. Can you hear me?
Yes.
Okay. So thanks a lot for for this nice introduction to your method. In the end, you showed the results for the C3 case.
Mm-hmm.
And so if I got it correctly, you first contracted the tensor network exactly for a small system. And you showed how the precision increases when you have more auxiliary fields. How does this look like for the Monte Carlo case? So how many layers did you have there? Or do you have something similar where you can really study how you converge?
The plot on the bottom is with Monte Carlo.
And how many layers did you have there? Or don't you use something like the layers?
Four.
Okay. So it's comparable to the previous plot with the highest precision.
Yeah, the idea here is that if you have a state that doesn't fit, you can hardly ever approximate it with Monte Carlo. So it's kind of a bit of a disentangling operation between the algorithmic problematic, so having a variational Monte Carlo procedure that has to actually minimize a given state, and evaluating the state on its own. So I can, of course, show you Monte Carlo data where we have only one layer, and you will see that this kind of quadratic dispersion, or this quadratic going up on the left side as well, because if the state doesn't fit, Monte Carlo can hardly do anything about it. So this was kind of this two-step procedure. First, see that the state fits for a small system, and then see that the Monte Carlo actually converges as well, because they're kind of two independent problems.
Sure, you can't be better than your ansatz.
Exactly.
Did you also make a study just with the Monte Carlo for the large systems and study if you also converge there, if you use more layers?
Well, yes, we converge kind of, so it's getting more complicated, of course, if you have larger systems, and you have to numerically optimize it. You have more parameters in the multi-layer case. So that's why on the left side of that bump, you have data that is a bit worse than on the right side, because there our state is fitting obviously better. But yes, so the Monte Carlo here is converging in the sense that if I do multiple runs, I will get similar outcomes.
Okay, thanks a lot.
You're welcome.
Okay, are there further questions? If not, then let's thank Erez again for the talk.
Thank you.